Have you ever looked at one of those incredible limestone caves, like Luray Caverns or Mammoth Cave, and just wondered, how? How do those amazing shapes actually form?
Yeah, it seems almost magical, doesn't it?
It really does. Or maybe think about something medical, like how an X-ray contrast agent, barium sulfate, is okay to swallow, even though we know barium ions are pretty toxic.
Right, it seems counterintuitive.
Well, it turns out there's this whole intricate chemical dance happening just beneath the surface, and today we're taking a deep dive into exactly that.
We are. We're going to unpack the world of solubility and
Right.
complex iron equilibria.
Think of it like understanding why some stuff dissolves super easily, like sugar in your tea, while other things barely seem to dissolve at all.
And maybe more importantly, how we can sometimes, nudge things chemically to make even the stubborn ones dissolve
Yeah.
or precipitate out when we want them to.
Exactly.
And what's really fascinating, I think, is how these principles, which can seem a bit abstract in a textbook,
Mm.
actually control so much of what we see around us.
Mm.
I mean, a huge amount of chemistry, especially in nature and in our bodies, happens in water, in aqueous solutions. So understanding how salts dissolve or don't dissolve, and how these things called complex ions form, it's fundamental.
Absolutely.
So our mission for you today really is to walk you through these key ideas from the chemistry chapter. We want to show you not just what happens, but why it matters.
And how you can kind of get the logic, right?
Yeah.
Even without needing to see equations drawn out, we want to make these complex ideas really click.
Precisely.
Yeah, getting these principles down is so foundational, and that's what we're aiming for, pulling out the most important nuggets of knowledge, giving you a clear path, sort of a shortcut to really understanding the stuff without getting lost in all the details.
Okay, so where should we start?
Let's start right at the beginning. Solubility.
Mhm.
Simple definition, right? It's just a substance's ability to dissolve in a solvent, usually water for our purposes.
Like table salt, sodium chloride, dissolves easily. Sugar, sucrose, dissolves easily.
Right. But then you have things like, oh, calcium sulfate. That can build up a scale inside boiler pipes. That's also about solubility, or rather, its limits. Not always a good thing in that case.
No, definitely not. And it
Yeah.
banks us straight to the core idea for quantifying those limits, the solubility product constant, or KSP.
KSP?
Okay, it's simply an equilibrium constant. Specifically, it's for the process where a solid ionic compound, one that's only slightly soluble, dissolves in water.
So, like, if you put solid calcium fluoride, KF2, in water.
Exactly. It dissolves slightly, forming calcium ions, K2 plus here, and fluoride ions,
Mm.
F. The KSP expression involves the concentrations of only those dissolved ions. Remember, pure solids don't appear in equilibrium expressions.
Ah, good point.
So KSP plus F2, that exponent 2 comes from the stoichiometry, 2 fluoride ions for every 1 calcium ion.
Okay, so KSP is like a fixed number for that salt at a certain temperature?
Yes, precisely. Think of it like a saturation limit for the product of the ion concentrations. It tells you the maximum ion concentration product the solution can handle before the solid starts to reform or precipitate. It's that point where dissolving and precipitating are happening at the same rate.
That's a great way to put it, a saturation limit. And it highlights something really crucial you mentioned in the outline. KSP is the constant, but solubility is more like the position you reach.
Exactly. KSP is fixed, like the speed limit. Solubility is the amount that actually dissolves to reach that equilibrium state.
So if I grind up the solid really fine or stir it like crazy,
You'll reach the equilibrium faster, sure. You'll
Yeah.
hit that saturation limit quicker, but you won't change the limit itself, the KSP. Nor will you change the amount that's dissolved once you get there, the solubility in pure water.
okay, that distinction is key. KSP is the rule, solubility is the result under specific conditions.
You got it. And this isn't just theory. It has real-world impact. Think about tooth decay.
Right, you mentioned that.
Your tooth enamel is mostly a mineral called hydroxyapatite. Bacteria in your mouth produce acids, especially if you eat sugary things.
Mm-hmm.
These acids, the H+ ions, react with the hydroxide part of the enamel, causing it to dissolve. That's a cavity starting.
Okay.
Now, fluoride comes in from toothpaste or water. Fluoride ions can replace the hydroxide ions in your enamel, forming something called sclerapatite and also calcium fluoride.
And these are different how?
They are significantly less soluble in acid than the original hydroxyapatite. Their KSP values, effectively, are lower under acidic conditions. So fluoride makes your teeth more resistant to acid attack.
Wow, okay. That's everyday chemistry right there.
It is. Or think about that barium sulfate for X-rays. Beta-4, barium ions, B2 plus ions are definitely toxic.
Yeah, I remember that.
But barium sulfate has an incredibly tiny KSP value, It's practically insoluble. So when you drink this suspension, yes, there's solid BaSO4, but the actual concentration of dissolved B2 plus ions in your system stays extremely low, way below toxic levels.
So the low solubility makes it safe. That's clever.
It's a fantastic application of equilibrium principles.
Okay, so KSP is this fundamental constant. But the really interesting part for me is how we can actually use these KSP values to, quantify things, to predict how much dissolves.
Right, moving from the concept to the numbers.
Yeah.
And again, we will get lost in the calculations themselves, but the logic is important.
Let's walk through that.
Okay, so you can calculate KSP from solubility. If you experimentally measure how much of a salt dissolves, say copper, ibromide, cubri, dissolves to the tune of 2.0 by 10 to 4 moles per liter.
That's its molar solubility.
Correct. Since cubri gives 1 Q plus ion and 1 Br ion, their concentrations at equilibrium will both be 2.0 by 10 4m.
Okay.
So KSP is just Q plus Br, which is 2.0 by 10 to 4
Yeah.
times 2.0 by 10 to 4, or 2.0 by 10 4 2.
Simple enough for a 1.1 salt, but what if it's like that bismuth sulfite example, bi2s3? That dissolves into 2 bismuth ions and 3 sulfite ions.
Exactly. That's where stoichiometry becomes critical. If you know the molar solubility by 2s3 is, let's say, x moles per liter.
Then the concentration of bi3 plus ions isn't x, right? It's 2x.
Precisely. And the concentration of S2 ions is 3x.
Okay, I see.
So when you plug those into the KSP expression, KSP equal by 3 plus 2s23, it becomes 2 by 2 times 3 by 3. That works out to 108 by 5.
Whoa, x to the 5th power. That's a huge difference from the simple x squared we saw for Q.
Massive difference. And that's the key takeaway. Those stoichiometric coefficients turn into exponents in the KSP expression.
And this matters when comparing salts.
Absolutely, critically. You can only directly compare KSP values to predict relative solubility if the salts produce the same number of ions, like AgCl, KSP, KO4, they all produce 2 ions. For those, bigger KSP means higher solubility. Simple.
But if they produce different numbers of ions, like comparing, say, CuS2 ions with Ag2S3 ions or Bi2S3 5 ions.
You cannot just look at the KSP values.
Yeah.
A salt with a smaller KSP might actually be more soluble if it produces more ions per formula unit because of how that X gets raised to higher powers. You have to calculate the molar solubility for each one individually if you want a true comparison.
That's a really important warning. Don't just compare KSP values blindly.
Definitely not. It's a common mistake.
Okay. So far, we've mostly talked about dissolving things in pure water, but real life isn't usually pure water, is it? What else affects solubility?
2 major factors we need to consider are the common ion effect and pH.
Right. Let's take the common ion effect first. What's that about?
Okay, imagine you have your slightly soluble salt, say silver chromate, Ag2CrO4, sitting in equilibrium with its ions, Ag plus and CrO42.
Got it. The KSP limit has been reached.
Now, what happens if you add something else that also contains one of those ions, like maybe you dissolve some silver nitrate, AgNO3, into the solution?
Well, silver nitrate is soluble, so it adds a bunch of Ag plus ions, which are already part of the silver chromate equilibrium. They're common ions.
Exactly. You've just increased the concentration of one of the products, Ag plus. So what does Le Chatelier's principle say will happen?
The equilibrium will shift to counteract the change. It'll shift back to the left towards the solid.
Precisely. Adding the common ion, Ag plus, forces the equilibrium, Ag2CrO4 equals 2Ag plus AQ plus CrO42AQ, to shift left. This means more solid Ag2CrO4 forms, and the solubility of silver chromate decreases.
So adding a common ion makes a sparingly soluble salt less soluble.
Yes. It's like that crowded dance floor analogy again. If more silver dancers, Ag plus ions, show up from the silver nitrate, some of the silver dancers already on the floor from the dissolving Ag2CrO4 have to leave and sit down precipitate to keep the crowd density, the AGP product, constant.
Okay, that makes sense. Common ion effect reduces solubility. What about pH? How does that play a role?
pH can have a huge effect if one of the ions involved in the solubility equilibrium is acidic or basic.
Meaning, if the anion is the conjugate base of a weak acid.
Exactly. Or if the cation is the conjugate acid of a weak base, though anion effects are more common here.
Right.
Let's take magnesium hydroxide, MgOH2. That's milk of magnesia. It's not very soluble in water.
Right.
But what happens when it hits your acidic stomach? Your stomach has low pH, meaning lots of H plus ions. The hydroxide ions, OH coming from the dissolving MgOH2, are basic. They react readily with the H plus ions from the stomach acid to form water, H plus plus OH, H2O.
Ah, so the acid removes the OH ions from the equilibrium.
Yes, it pulls the OH concentration way down. According to Le Chatellier, if you remove a product, the equilibrium MgOH2 plus AQ shifts to the right to replace it.
Meaning more MgOH2 dissolves.
Exactly. Magnesium hydroxide is much more soluble in acidic solution than in neutral water. The same logic applies to salts, like silver phosphate, Ag3PO4. The phosphate ion, PO43, is the conjugate base of a weak acid, HPO42, so it reacts with H plus A. This makes silver phosphate more soluble in acid.
But what about something like silver chloride, AgCl?
Good question. Chloride ion, Cl-Atia, is the conjugate base of HCl, which is a strong acid.
Meaning Cl is a terrible base. It doesn't really want to react with H plus.
All right, so changing the pH doesn't significantly affect the Cl concentration. Therefore, the solubility of HgCl is pretty much independent of pH.
Okay, so solubility increases in acid if the anion is a decent base.
That's the main idea. And this brings us back full circle to those limestone caves.
KCO3, calcium carbonate.
Right. Carbonate, CO32, is the conjugate base of a weak acid, HCO3 bicarbonate. Natural rainwater picks up CO2 from the air, forming carbonic acid, H2CO3, which is weakly acidic.
So the groundwater becomes slightly acidic.
Yep. That slightly acidic water dissolves the calcium carbonate limestone much more effectively than pure water would, because the H plus reacts with the CO32. That's how the caverns get carved out over millennia.
And the stalactites and stalagmites.
That's the reverse. When that dissolved calcium bicarbonate solution drips from the cave ceiling, it comes into contact with the air. CO2 gas comes out of the water droplet.
Losing CO2 makes it less acidic. The pH goes up.
Exactly. As the pH rises, the equilibrium shifts back towards the solid KCO3. It precipitates out of the droplet, very slowly building up those beautiful formations.
Wow, it's just ongoing pH-driven solubility changes.
Pretty amazing, isn't it?
So we know how to make things dissolve, sometimes using acid. Can we also make things undissolve on purpose? Is that precipitation?
That's exactly what precipitation is. And it's an incredibly useful tool for chemists, especially for separating things.
How do we predict if something will precipitate?
We use something called the ion product, Q. It looks just like the KSP expression, but instead of using equilibrium concentrations, you plug in the initial concentrations of the ions right after you mix the solutions before any precipitation has happened.
Okay, so Q is like the situation right now, and KSP is the limit.
Perfect analogy. If Q, KSP, the current ion product is too high, the solution is supersaturated, precipitation will occur, reducing the ion concentrations until Q equals KSP. If Q, KSP, the ion product is below the limit. The solution is unsaturated, no precipitation will occur. More solid could still dissolve if present. If Q equals KSP, the solution is exactly saturated. It's at equilibrium.
Got it. Q tells us if we've exceeded the KSP limit.
Right. And when precipitation happens, especially if Q is much larger than KSP, the reaction often goes almost to completion. We usually assume it precipitates completely first, figure out the limiting reactant, and then use KSP to calculate the tiny concentration of ions that remain dissolved at equilibrium. It often involves the common ion effect from any excess reactant left over.
Okay. And you mentioned using this for separation.
Yes, selective precipitation. This is really clever. If you have a mixture of different metal ions in solution, you can often find a reagent, an anion, that will form a precipitate with only one or some of those metal ions, especially if their KSP values are very different.
Like the silver and lead example with iodide.
Exactly. Silver iodide, AgI, has a much smaller KSP than lead iodide, PbI2. So if you add iodide ions slowly, the AgI will precipitate out first at a very low iodide concentration. You can filter that off, then add more iodide to precipitate the PbI2.
You can pick them off one by one based on their solubility.
That's the idea. And a really versatile anion for this is the sulfide ion, S2. What's neat about sulfide is that you can control its concentration very effectively just by controlling the pH.
How does that work?
Well, sulfide ion is very basic. It comes from the weak acid H2S, hydrogen sulfide. In a strongly acidic solution, low pH, the equilibrium H2S equals 2H plus S2 is pushed far to the left. This means the concentration of free S2 ions is very low.
Okay.
Under these acidic conditions, only the most insoluble metal sulfides, those with extremely tiny KSP values, like copper 2 sulfide CuS or mercury 2 sulfide HCS, will precipitate.
So low sulfide concentration picks off only the least soluble sulfides.
Right, but now if you make the solution basic, high pH, low H+, the equilibrium shifts to the right. The concentration of free S2 ions becomes much higher.
And with more sulfide available.
You can now precipitate metal sulfides that are more soluble, ones with larger KSP values like manganese sulfide MnS or nickel sulfide NaS, which wouldn't precipitate in the acidic solution.
That's really elegant, using pH to fine-tune the concentration of your precipitating agent.
It is. And this precise control, using solubility differences, common ions, pH, and sulfide precipitation, is the foundation of qualitative analysis.
Right, the classic chem lab scheme to figure out what ions are in an unknown mixture.
Exactly. It's a systematic approach. You separate carnications into groups based on these solubility rules. Group 1, add HCl. Only Ag plus A, Pb2 plus AAHE, and Hg22 plus precipitated chlorides because their chlorides are insoluble. Filter them off. Group 2, take the remaining solution, make it acidic, and add H2S. The very insoluble sulfides like CuS, Bi2S3, HGS precipitated. Filter again. Group 3, make the solution basic, add more H2S. Now the slightly more soluble sulfides, MnS, NAS, CFS, ZnS, and some hydroxides, AlOH3, CrOH3, precipitate. Filter. Group 4, add carbonate ions, insoluble carbonates like KCO3, BaseO3, precipitate. Group V, what's left? Mostly alkali metal ions, Na+, Can+, and ammonium, NH4+, which generally form soluble salts. These are often identified by things like flame tests.
It's like a chemical flow chart, separating ions based purely on their solubility behavior under different conditions.
Precisely. A beautiful application of equilibrium principles.
Okay, there's one more major topic we need to cover. Complex ions. You mentioned these earlier. They sound, well, complex.
They can seem that way, but the idea is straightforward. A complex ion is basically a central metal ion that has formed bonds with several surrounding molecules or ions called ligands.
Ligands, like ammonia or chloride ions.
Exactly. Ligands act as Lewis bases. They have a pair of electrons they can donate to form a coordinate covalent bond with the metal ion, which acts as a Lewis acid. Water, H2O, ammonia, NH3, chloride, Cl, cyanide, Cn, are all common ligands.
And they surround the metal ion.
Yes, in specific geometries. The number of ligands attached is the coordination number, often 2, 4, or 6. Think of things like AgNH32+, or QNH342+, or FDCN63. These are all complex ions.
Okay, why are they important for solubility?
Because forming these complex ions can dramatically increase the solubility of solids that would otherwise be insoluble. They form with formation constants, KRS, which are equilibrium constants for adding the ligands. Often these KO values are very large, meaning the complex ion is very stable once formed.
How does that help dissolve things?
Think about our old friend, silver chloride, AgCl, insoluble in water. But if you add concentrated ammonia solution...
The ammonia molecules are ligands.
Yes. They react with the free Ag plus ions in solution, the tiny amount that does dissolve from AgCl, to form the stable complex ion, diamine silver I, AgNH3 plus I.
So the ammonia essentially grabs the Ag plus ions out of the solution.
It ties them up, exactly. By drastically lowering the concentration of free Ag plus ions, it pulls the original solubility equilibrium, AgCls, Ag plus AQ, plus ClAQ, far to the right, according to Le Chatelier.
Causing more AgCl solid to dissolve to try and replace the Ag plus that's being complexed by the ammonia.
You've got it. The ligand acts like a sink for the metal ion, constantly removing it from the simple solubility equilibrium and thereby promoting more dissolution. It's like that shy person at the party analogy. Again, the ammonia ligand is the outgoing friend who pulls the shy silver ion onto the dance floor.
That's a fantastic mechanism. So complex ion formation can overcome low KSP values?
Absolutely. It's incredibly powerful. Remember aqua regia, that nasty mix of nitric and hydrochloric acids used to dissolve gold and platinum?
Yeah.
It works partly by forming stable chloride complex ions, like AuCl4. Combine that with the oxidizing power of nitric acid, and you can dissolve even very unreactive metals. We even use complex ions in qualitative analysis to separate ions within a group.
Like within group I, the insoluble chloride.
Yes. After precipitating AgCl, PbCl2, and Hg2Cl2, you can treat the solid mixture. Lead chloride, PuCl2, is unusual because its solubility increases significantly with temperature, so you can dissolve it in hot water. Silver chloride, AgCl, as we just discussed, dissolves in aqueous ammonia because it forms the AgNH3 complex. If you then add acid back to that solution, the H+ reacts with the NH3, destroying the complex and causing the AgCl to precipitate out again, confirming silver was present.
Clever.
And mercury chloride, He2QCl2, does something unique with ammonia. It undergoes a disproportionation reaction, forming elemental mercury, which looks black or gray, and a white compound called mercury imidochloride, HgNH2Cl. That distinctive gray-black precipitate confirms mercury.
So you use heat, ammonia complexation, and unique reactions to tell those three apart.
Exactly. It's all about exploiting differences in their chemical behavior, much of which relates back to solubility and complexation.
Wow. Okay, that's a lot, but it really connects together.
It does. We've gone from basic solubility in KSP, looked at how common ions and pH shift those equilibria, seen how to use precipitation selectively, and finally explored how complex ions provide another powerful way to control solubility.
It really paints a picture of how dynamic these seemingly simple dissolving processes are.
Absolutely. And these aren't just abstract concepts, right? They explain tooth decay prevention, how medicines work, cave formation, how we test for ions. It's a chemistry happening all around us and inside us.
So, what does this all mean for you listening in? Well, the next time you see water dripping in a cave, or use a fluoride rinse, or heck, even just watch salt disappear into soup, you'll have a much deeper appreciation for the intricate dance of ions, equilibria, and solubility happening right there.
It's a constant chemical conversation, even in things that look completely solid or stable.
It really is. It's a great reminder that the world at the molecular level is always in motion. Thank you so much for joining us on this deep dive.